Hello calculus fans, and welcome to section 4.1 where we talk about maximum and minimum values. Some of the most important applications of calculus are optimization problems, where we are required to find the best way to do something, which usually means the fastest way or the least expensive way. So as an example, what are the dimensions of a pop can that minimizes manufacturing costs but still holds 12 ounces? These problems can be reduced to finding the maximum or minimum values of a function that models the particular situation. So before we get started, we've got some definitions we have to talk about. So if we let c be some number in the domain D of a function f, so c is just some number in the domain of this function, then f of c is one thing we need to know about is the absolute maximum. Some calculus resources call this the global maximum, but our book and most other textbooks will call it the absolute maximum. And what that means, if it's the absolute maximum of the function on this domain, it just means that f of c is greater than or equal to f of x for all other x's in the domain. So it's the absolute maximum value. Now also note f of c, make a little note here, this is a y value, right? This is the y value, so it's the value of the function. So c is not the absolute maximum, f of c is, right, the y value. Just that c would be the x-coordinate where that occurs. Okay, and then also we could have an absolute minimum value or a global minimum of the function on this domain if f of c is less than or equal to f of x for all other x in the domain. Okay, so absolute maximum and absolute minimum, these are also referred to as extreme values. So these two will be referred to sometimes as extreme values, which makes sense because they are the largest and the smallest values the function takes on in the entire domain. And that's basically what the note says here. These are the maximum or minimum values of the function in the entire domain. Okay, a couple other definitions we have. The number c, or the number f of c. Again, notice this will be a y value, right? The number f of c, which would be the function's value at c, is a local maximum, or sometimes referred to as a relative maximum, if f of c is greater than or equal to f of x when x is near c. Okay, so locally, this is the largest value, but maybe not globally. Maybe not the absolute maximum, but locally it's the maximum. And also, of course, we could have a local minimum if f of c is less than or equal to f of x when x is near c. Okay, so just like a quick little example here. If we've got something that goes like this, you can see that right around here, locally, this is a maximum. So this would be a local maximum, but it's not the absolute maximum. The absolute maximum would be up here, right? Okay, so that's the general idea, and we'll get into more details about that in just a second here. Okay, and then the other note here, these are the maximum or minimum values of the function in some interval. Okay, so let's look at an example. Maybe I'll kind of use the example I was just using, but I'll make a little better version of it. Okay, so if you just make a quick sketch, something like this, and let's say we've got this graph that goes like this, and we can see that as you're around this x value here, around this x value, the graph or the function has a little peak here. So like right here at this peak, this would be a local maximum at this peak, local max. Now also, there's this little valley here. This would be a local min. And there's a local min right here. And wherever this little minimum is, that'd be the local minimum, local maximum. Now over here, there's another local minimum, right? Like locally, if you're around this x coordinate here, around these x values, this is a local maximum. But this one's not only a local maximum, it's also the absolute maximum, right? This is also the absolute maximum. Now I've got a local minimum here. What about an absolute minimum? Is there going to be an absolute minimum for this graph? There won't be, right? Because these both sides go to negative infinity. So with this graph, there is no absolute minimum. Okay, makes sense? So let's try another example. This one, though, is going to come out of the book. So I'm going to try to sketch this picture from the book as best as I can. This one is, I'm going to take from the book page 286, number 3, and this is from the 9th edition. If you've got the 8th edition, it's going to be on page 283, number 3. Okay, it's the same problem. And it looks like this. Okay, so here is a little sketch of the drawing from the book. Of course, the one in the book is a lot nicer, but it looks something like this. You say we've got these points A, B, C, D. I'm not sure what's going on with RS. I don't know why we kind of did a restart at R, but anyway, this is what we've got. And they want us to identify these points as any of those four definitions that we just talked about. So absolute max, absolute min, local max, local min. And then there's some little quirk that I'm going to mention to you that is not important, but that comes up in problems like this problem, and maybe one, maybe two in the homework in this section, and that's it. And it's just a little quirk about the definition of local max and local min. But we'll talk about it as we go. So, well, actually, we need to talk about it right now. So let me make a little note here. Again, it's not going to matter at all in the big picture, but let me just make a note here. Okay, so in the Stewart textbook, in the James Stewart textbook that we use, there will be no local max and no local mins at endpoints. Okay, so when you're at an endpoint where this graph just ends here, there's not going to be a local max or min at the endpoints. Absolute max and mins work, but not local. And the reason for this, it's hard to see now in the current version of the textbook, but in the older versions of Stewart, the local max and min were defined using open intervals, and with a little bit more of a rigorous definition. So as I mentioned before, the way calculus is taught now, we have a lot more applied problems. We have access to technology, so we can do a lot more realistic applied problems. But in the past, before graphing calculators were everywhere, it just seems like calculus was taught with more theory and less practical problems. And so one of the older versions, by the definition using open intervals, then local max and local min didn't exist at endpoints since open intervals don't exist there. So it is super, super not important. Really, it takes so much time to explain it that it's almost not even worth explaining it. But otherwise, you'd wonder why some of the homework problems were, or maybe one or two of them, where you get kind of weird answers. So that's it. So basically, when it comes to local max and local min, anything where the graph ends at an endpoint, they won't exist. And it's just because of a definition from an older version. So just kind of keep that in mind, and that's it. And really just kind of carry on. It's not a big deal. It's not going to affect the applied problems at all. It'll just affect maybe one or two homework problems. So with that in mind, as we go along here, we can see that this point right here, locally, this is a minimum, right? Even there's this weird kind of like kink in the graph or a little spike in the graph, but that would be a local minimum there. So I'm going to just point out this point here would be I'll just say L min, a local minimum. Then we can see right here we've got a local maximum up here. So around this value of C, the function takes on a maximum. So locally, that's a maximum. So that Y value there would be a local maximum. Now again, over here, locally, this is the maximum, but local max, local min, they don't exist at endpoints, so we're not even going to count it. Over here, there's really nothing here. Maybe an inflection point, but we haven't even talked about that yet, so it's really nothing. It's none of those, at least the 4 definitions we just talked about. Now down here, you can see we've got a local minimum, right? So locally, that is the minimum. Local min. But it's also got something else. It's also the absolute minimum. This is the lowest value that this function takes on over this domain from A to S, right? So it's not only a local minimum, it's also the absolute minimum. It's both local minimum and absolute minimum. Okay, then up here, this is the highest point in the graph. This is an absolute maximum. Okay, it's an absolute maximum. Why is it not a local maximum? Again, just over here, local max, local min don't occur at endpoints. Okay. So also just keep in mind these maximums and minimums are the Y values, right? You want the values that the graph or that the function takes on. Okay, not these A, B, C, D, R, S. That's maybe where they occur. Those are the X coordinates. But the local max and local mins are the peaks and the valleys in the graph of the function. So just to make it clear, if somebody asks you what the local max is, we would say the local max is f of s, right? It's not s. It's not s. It's f of s. Or you could say it's the point s comma f of s, right? That point. But we definitely need the y coordinate in there. Okay, you guys ready for another example? So if you go ahead and put a few XY planes here, and we'll make some drawings and we can talk about these. So example 3, let's say we've got a graph of y equals x squared. If you've seen this one in your life more than 1,000 times, raise your hand. Okay, probably everybody, right? This one is everywhere. Y equals x squared. The parabola goes through the origin like this. So if we're going to looking for local max, local min, absolute max, absolute min, well, I think we can agree there's no maximum, right? There's no maximum with this one. So there's no max, no absolute max, no local max. What about this right here? What's this? Well, you can see locally this is a minimum, right? My graph isn't the best. It looks like it's flattened out right there, but it doesn't. This is just my bad drawing. So we know it just touches there and curves back up, right? So we know that there's a local minimum here. But isn't there also an absolute minimum? There's both, right? That's locally it's the minimum, and absolutely it's the minimum. It's the minimum on the whole thing. Okay. So what about if we change y equals x squared a little bit and we just define this little piece of it here? Okay, well, now there are only endpoints, right? So there's not going to be local anything, right? By the definition we're using for local max and local min, they don't exist at the endpoints. Okay, so there's no local anything. Let me just write these down. So there's no local min, no local max. Okay, so what about that point right there? What is that point? Well, that point is going to be the absolute max, right? And, okay, get back here. I don't know why it does that. What about this one? absolute minimum, right? So you've got an absolute minimum, absolute maximum, but no local anything. Okay, one more little tweaking of this picture. Let's see, we've got an open here and an open here. Well, there's endpoints here, so there's no local max, no local min. What about absolute? What's the absolute minimum of this? It's not defined at 0. What's the number closest to 0? You don't know that number? There is no number, right? Whatever number you pick, your friend could pick one smaller just by dividing it by 2, right? So there's no local or absolute minimum, and same thing up here. We've got a hole there, so there is no local max or absolute max either. There's really nothing here. None of those 4 new definitions are here. There's just nothing. Okay, so hopefully that is making sense. We'll move on to something called the extreme value theorem. Okay, so this is one of those theorems that it's not shocking. Like I'll mention it to you, we'll draw a picture, and you're going to be like, yeah, this seems completely reasonable. It seems like it couldn't not work. So it's one of those kind of theorems, so it's not shocking. We'll use it when we're looking for absolute max and absolute min. The fact that this theorem exists will allow us to find these numbers with confidence. And some of you who are super lucky, if you take Calculus 5, probably only math majors would do this, maybe math minor. And in that class, it's like, some places will call it analysis, or some will call it advanced calculus, but that's when you prove all these theorems. Then you'll spend some more time on this. But for us, we're just going to use it right here. And to make sense of it, I'm going to draw a picture first, okay? I'll draw a picture first and then explain it. Okay, so here's what it says. If f is continuous on a closed interval AB, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in this interval AB. So we've got to have a continuous, right? We're in calculus, all the functions we're concerned about for the most part are continuous. So this function is continuous, so there's no holes, no jumps, no gaps, anything like that. It's continuous on this closed interval AB. So this just says it has to attain an absolute maximum and an absolute minimum at some points in this interval AB. You can see right here, okay, we've got this point right here. We'll say this point C, there's a maximum here. You can see like the maximum occurs at this peak, this little peak there. So where this slope of the tangent curve is 0 here, there's a maximum value. And likewise, where the slope is 0 down here, you'll find this minimum value D. And you could, think of any sketch you could come up with, and this is always going to be the case. Even a horizontal line, it just means that the max and the min are equal to each other, right? But basically, the extreme value theorem tells us that a continuous function on a closed interval will have a maximum value and a minimum value. So when we're trying to optimize these functions, we know that what we're looking for exists. The extreme value theorem doesn't tell us how to find these things, it just tells us that they exist. So now let's talk about how to find these maximums and minimums. First up, we have to define something called a critical number. So a critical number of a function is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. Okay, now of these two, this is by far the most important case. So usually, if the derivative doesn't exist at a point, it's not going to be a point that we're interested in when it comes to optimizing problems. But But the definition of a critical number is the point C such that either of these occurs. So we'll have to check for these quite often. Okay, so the reason this one's important is because this is telling us that the derivative of a function at this point is 0. So if the derivative is 0, geometrically that means the slope of the tangent is 0. And if you think of that picture that we just looked at with extreme value theorem, where the tangents are 0, that's where the peaks and the valleys of the function occur. So that is where you can find the critical, or you find your maximum or minimum values. Okay, so this talks about here the derivative not existing. So how can f prime of c fail to exist? Okay, so for this one we talked about this quite a bit in section 2.8. So I could say see the section 2.8 notes. But a quick review basically is, how can the derivative fail to exist? Well, if we have spikes or kinks or discontinuities. Well, if any of those happen, then typically the derivative will not exist at those points. So a spike could be something like, if you have like y equals x to the 2/3, and it goes like this, as this little spiky point to it. And if you zero in on this point, it never flattens out. It's always going to be kind of a spike. Or a kink, sometimes like absolute value functions will have like a point to them like this, where again you zoom in on it, it never flattens out, it's always a point. Or discontinuities, you have a function that goes and then stops and jumps up and continues on, or even just a hole in the graph. At any of those points, you're not going to have a derivative at those points. So again, if you want more information, just look at what we talked about in section 2.8. Okay, but for the most part, these aren't going to be as much of an issue. We're really going to be concentrating on finding out where the derivative is 0. Okay, so that'll be the one we'll focus on the most. There's also a little note here. You have to just be aware. It says, if C is a critical number, f of C is not necessarily a local max or local min. Now, it normally will be, but it doesn't have to be. So as an example, let's say we've got f of x equals x cubed, and you're saying, okay, I'm going to find the critical number, so I'm going to take the derivative, set it equal to 0. All right, so I'm going to take this derivative, set it equal to 0, and then solve. So if 3x squared equals 0, that means x equals 0. So this is a critical number. X equals 0 is a critical number. But if you think of the graph of y equals x cubed, it goes like this, right? Y equals x cubed goes like this. So at 0, you've got a critical number, but it's not a max or a min. It flattens out just for an instant, right? But it's not a max or a min. So if you know that C is a critical number, it doesn't mean that you necessarily have a local max or local min. Okay, normally it will, but there are exceptions. So in this case, there is no max or min, no local max or local min. Again, I'll just use the L there to make it a little easier. There's no local max or local min at x equals 0, even though x equals 0 is a critical number. Okay, we just had a new definition, critical numbers, so I know what you're thinking. Come on, Kurt, stop doing all the work and let me try one. I know, I'm a bit of a mind reader. So here is your chance. Find the critical numbers of this function. So we got a polynomial. So we need to take the derivative, right? Take the derivative, set it equal to 0, and solve. And also take the derivative and ask yourself, is there any place where the derivative doesn't exist? Okay, so try this one out, and then press play again. And let's see how you did. Okay, so hopefully what happened is you took the derivative, you said f prime of x equals 3x squared plus 2x minus 1. We set this equal to 0. Okay, now remember, this is a second degree equation we're solving. We have 100% chance of solving this because we have a tool that works every single time with any second degree equation, right? It'll either solve it or we'll know that a solution in the real number system doesn't exist. We would need like complex numbers or something, right? What is that we can use 100% of the time with a second degree equation? Quadratic formula. Yes, we can use a quadratic formula. But some second degree equations can be solved with another method. Some, but not all. Quadratic formula works on all of them, but what works on some of them? What else could we do? Starts with an F, rhymes with actor. Oh, that was too much of a hint. Factor. You're right. That was too much of a hint. So this one does happen to factor. So what we could do, instead of the quadratic formula, we could factor this one and solve it that way. So remember, as a Calc 1 student, we absolutely have to be able to factor these or it's going to be a long semester. So if you're rusty on factoring trinomials, you really should take some time, refresh your memory so that you can factor these. Right? AC method or the standard guess and check method. There's plenty of videos around and you can get a little practice. But basically, we want to do the FOIL method backwards, right? First times first has to be 3x squared. So there's not really a lot of choices here. X times 3x. Last times last has to be a -1. I'm just going to think of it as 1 though, just while we're doing this. So I'll put a 1 and a 1. And then, of course, we know that when I multiply outside times outside and inside times inside, that has to add up to positive 2x. So that means I'm going to go plus 1 here and -1 here, because then we'll go -x plus 3x, which give us plus 2x. Okay, so the reason we can factor to solve is once we're here, we have the zero product property from algebra. It says if I multiply two numbers together and I get a 0, one of these is going to have to be 0 for sure, right? And that only works for 0. If something times something is 0, one of these somethings has to be 0, and it could be either one of them. So it could be that x plus 1 equals 0, or it could be that 3x minus 1 equals 0. So if x plus 1 equals 0, that means x equals -1. And over here, if I add 1 to each side, I get 3x equals 1, or x equals 1/3. Okay, so that means that these two are critical numbers. So both of these are critical numbers. X equals 1. Oops, x equals -1, and x equals 1/3. Okay. So hopefully that's making sense. And now we look over here, and this one's getting a little weirder, right? This is pretty straightforward. Polynomial. This one might be a little more work. But I know you guys are always up for the challenge. So let's try this one. Find the critical numbers of this function. Oh, I should have mentioned also back here. I didn't mention it, but I'm sure you guys noticed. This derivative, it's a polynomial, so it exists everywhere, right? There is no place where the derivative does not exist. There's no value you can plug in for x here and make it not exist, right? So remember, there's critical numbers occur at two places. One place is where the derivative is 0. The second place is where the derivative does not exist. But in this case, our derivative exists everywhere, so we don't have to worry about that. So these are the only two critical numbers. Okay, with that in mind, I wonder if this one, maybe we'll have a place where the derivative doesn't exist. We'll have to wait and see. Okay, let's go ahead and find that derivative. So g prime of t, power rule, right? We're going to have the 2/3 come down and multiply by the 5, so that will give us 10/3 t to the 2/3 minus 1, which is like 2/3 minus 3/3. So that would give us 10/3 t to the -1/3, right? 2/3 minus 3/3. Then again, power rule, 5/3 t to the 5/3 minus 3/3, which would be to the t to the 2/3. So we get plus 5/3 t to the 2/3 equals 0. All right, so I'm going to just rewrite this a second. Because this negative, when you have negative exponents and we're working with these, it's just kind of hard to work with. So isn't it true, let's get this off to the side, isn't it true that t to the negative 1/3 is the same as 1 over t to the positive 1/3? Right, from that rule from algebra class way back when. You can make this a positive down here. So because of that, if I have 10/3 times this, I really have 10/3 times this. So I could put the 10 and the 3 here, right? So really I've got 10/3. Maybe I'll just do it like this, just to be safe. 1 over, so 10/3 times 1 over t to the 1/3. And I could write this like 5 over 3 times t to the 2/3 over 1, right, if I really wanted to. So then we could say, okay, so really what we've got is 10 over 3t to the 1/3 plus 5t to the 2/3 over 3 equals 0. Now looking at this, this is g prime of t. Can you think of any values of t that would cause any problems here? You're probably going to say, yeah, if I plug a 0 in, so if this is g prime of t, I definitely can't figure out g prime of 0, right? Because if I plug a 0 in here, I'm going to division by 0. So because of that, just looking at this, g prime of 0 does not exist, right? I can't plug a 0 in. So t equals 0 is a critical number. All right, so we've got one critical number so far, t equals 0. But now we have to solve this equation. So I'm going to show you two ways to do it. But I think the easiest way to do it when you have something like this is you just subtract one of these so we can get a proportion. So I'm just going to subtract this from each side of this equation here. So that way we would have 10 over 3t to the 1/3 equals negative 5t to the 2/3 over 3. Right, just subtracting this from each side. But the nice thing from here is if we've got a fraction equal to a fraction, that means we've got a proportion. And with a proportion, the cross products are always equal. So if we multiply crossways, I would get, look at this one, I'm going to get this times this. I'm going to get negative 15t to the 1/3 times t to the 2/3. Negative 15, okay, off to the side here, t to the 1/3 times t to the 2/3. Don't we in this case add? We add these powers, we get t to the 3/3, which is just t. So this will give us negative 15t equals 30, right? Because we go this times this to get here equals this times this. This means we could just divide each side by negative 15. And we get t equals negative 2. So this is also a critical number. So we've got two critical numbers, t equals 0 and t equals negative 2. Now I'm going to show you another way we could have gone on this one. And we could have done it right from here. Now, if you really like factoring, you're going to like what I'm about to do. If you don't like factoring so much, you might not like it. But we could take this one and solve by factoring. So I'm just going to rewrite it down here. I don't think most people would do it this way, but just probably could be good for practice anyway. So let's just kind of see what happens if we do this. We can solve this by factoring. So think if you're factoring something out here. Like I'm going to do an easy example and then erase it. If I were factoring x squared plus 3x to the 5th, I was going to factor. Well, what's the greatest power of x I could factor out? That's going to be x squared, right? Let me just, to make it more, so it doesn't look so strange, let me put a 2 here. So you could say, oh, the greatest common factor is x squared, because between these two x values, this is the smallest one, right? So I could factor out an x squared. Okay, so keep thinking of that. And now look at this one. The smallest value here is t to the negative 1/3. So we can factor out t to the negative 1/3 because it's the smallest value. And also the smallest number is 5/3. So we could actually factor out 5/3 t to the negative 1/3. And if I did that, I'm going to right here get a 2 because 5/3 t to the negative 1/3 times 2 would give us here. So you get a 2 here plus, now here we have to think, okay, multiply through here, so the 5/3 is good. So t to the negative 1/3 times t to what makes t to the 2/3? Wouldn't this be t to the 3/3? Because then if I add negative 1/3 to 3/3, I'd get 2/3. And t to the 3/3 is just t. So basically I have this. And that means that either this equals 0, which can't happen, right? If this times this is 0, it means this equals 0. So 2 plus t equals 0, and t equals negative 2. So get the same thing. So this is just an alternate way. If you really like factoring, you could do it this way. Okay, I think most students would prefer this way, but just in case, there's another way to go. And now we are ready for the main point of this section. The main point of this section is to be able to find the absolute maximum or the absolute minimum values of a continuous function on a closed interval AB. And basically the steps are this, there's 3 steps. So what we do is we find the values of the function at the critical numbers of the function in this interval. Because the critical numbers are where all the peaks and valleys are, right? Critical numbers are where derivatives are 0 or where the derivative doesn't exist. But really, like I said, that won't be really an issue. That won't be something we're really looking for. So we're going to have to find the values of the function at the critical numbers because that's where all the derivatives are 0. That means the graph of the function flattens out at these areas. So they will usually be peaks and valleys. Not always. Remember that example, y equals x cubed? It wasn't a peak or a valley there. So it's a critical number, but not a local max or min. But basically, this will find all the values of the peaks and valleys, but it won't find the endpoints. Because if you just set a derivative equal to 0, and if your max or min value is at an endpoint, you won't find it that way. So then the second part is this. We find the values of the function at the endpoints. In other words, plug a and b into the function and find those. And then between these two, you're going to find the absolute max and the absolute min on that interval. And then step 3 just says that to find the largest value from steps 1 and 2. Well, the largest value from steps 1 and step 2 is the maximum value, and the smallest value from steps 1 and 2 is the minimum value. So step 3 is really 2 sentences combined in one, right? So largest goes with maximum, smallest goes with minimum. Okay, so that's what we have to do. We just look for the look at the critical numbers and then look at the values of the functions at the endpoint. So just as a quick example to see how these fit together, if you find the values of this function at the critical numbers, you're going to find all of these flattening out spots. So you're going to find this peak, this valley, and this peak. Now in this interval a to b, you're going to find the absolute maximum. This point right here, that point is the absolute maximum on this interval AB. But you won't find the absolute minimum because the absolute minimum is over here at an endpoint. So the only way you're going to find this absolute minimum, right, that's the absolute minimum on the interval AB. To find that, you have to do part 2. So part 1 will find all these peaks and valleys, and then part 2 will check the endpoints. And between these two, you will have the largest and the smallest values. So that's the basic idea. All right, so let's try one out. Example 6 says find the absolute maximum and absolute minimum values of f on the given interval. And this is kind of a typical question, and then we just list out a function. So let's try this one. All right, so let's try this one. We've got this fourth degree polynomial, x to the fourth minus 2x squared plus 3. And we're looking at this interval from -2 to 3. And we want to find the absolute maximum and the absolute minimum values of the function on this interval. So to do this, we need to find the critical numbers, right? Because the critical numbers will give us all the peaks and valleys. So that'll give us all the peaks and valleys of this graph. So we'll evaluate this function at those critical numbers. And then we'll also have to plug in the endpoints of the function into here. And we'll compare those values. The largest one will be the absolute maximum. The smallest will be the absolute minimum. And the extreme value theorem guarantees that there will be an absolute max and absolute min here because this is continuous, right? So let's go ahead and find f prime of x. So we have the power rule. We'll get 4x cubed minus 4x. And then just looking at this, we can see that there's no place where this derivative does not exist, right? This derivative exists everywhere. It's just a polynomial. So as far as the critical numbers go where the derivative doesn't exist, there are none of those. So we're going to have to just find out the critical numbers that cause the derivative to be 0. So we need to solve this, which we can definitely solve by factoring, right? There's a common factor, 4x. So you could factor out of 4x and get x squared minus 1 equals 0. And then that means that this, if this times this is 0, this is 0, or that is 0. And you could even factor this too. So it depends on how you want to solve this. You could factor this. This is a difference of perfect squares. You could get x minus 1, x plus 1, or you could just solve from here, right? So you could say, all right, so either 4x equals 0 or x squared minus 1 equals 0. If 4x equals 0, that means x equals 0. That's a critical number. And x squared minus 1 equals 0, that means x squared equals 1. Now x squared equals 1, when you take the square root of a square, remember, we're going to get two answers here. So we get x equals plus or minus 1. So these are the critical numbers right here. We've got three critical numbers. And then what we need to do is we need to check. We need to plug in the critical numbers into here, right? And I'm just doing the steps from above. And where it said how to find the absolute maximum and absolute minimum values. So we plug the critical numbers into the original function, then we plug the endpoints into the original function. Because these find the peaks and valleys of the graph. But if the max or min occurs at an endpoint, this won't find it. So we need to check the endpoints too. So basically, once we do this, we just go something like this. F of 0 equals, f of 1 equals, f of -1 equals, f of -2 equals, and f of 3 equals. Now from this point, it's just arithmetic. So what I would probably do, I would plug this in to my graph, in my graphing calculator. I'd plug this in for y1. Just go to plug this in for y1, and then go to the table, and I just plug in these values. Because you don't have to convince me that you can do arithmetic, right? You don't have to do this by hand. You can just plug these in. And if you do that, or if you just plug them in right here, the key is don't plug them in the derivative. It's an easy mistake to make. These are values of the function, right? F of 0. So f of 0, if I plug a 0 in here, I'm going to get a 3. That one's easy enough. You plug a 1 in here, you get 1 minus 2 plus 3, which gives you 2. If you plug a -1 in, you also get 2. If you plug a -2 in, you get 11. And finally, if you plug a 3 in there, you get 66. So to answer the question, I'm going to do a common mistake. Okay, I'm going to do a common mistake here. And let's say answer the question. I say absolute max equals 3. Am I right? No, it makes you very sad to see that up there, doesn't it? It's not true. The absolute maximum is not 3. The absolute maximum is the biggest number here. The biggest number here is 66, right? That's the absolute maximum. The absolute maximum value that this function takes on in this interval is 66. That's the absolute maximum, 66. What's the absolute minimum? 2, right? So the absolute minimum equals 2. You don't have to say 2 and 2, right? Sometimes students do that. Oh, it's 2 and 2. You don't need to say 2 and 2. Think if you did have to do that, and then somebody said, hey, what's the absolute maximum of the sine function? What would you say? 1 and 1 and 1 and 1? No, you wouldn't. You said the absolute maximum is 1, right? So absolute max equals 66. Absolute min equals 2. All right, so that should give you what you need. I just need to practice. The general idea is from that, just above this, right, just above this in the handout, it talks about to find the absolute max or absolute min. We just have to check. You have to find the critical numbers, plug those into the function, and then look at the endpoints, plug those into the function. So whenever you're looking for the absolute max or absolute min, you have this little list here where you plug in all the critical numbers and the endpoints of the function, and then you just pick the biggest one and the smallest one. All right, so kind of short and sweet this time. I know you guys like these long, drawn-out videos, so I apologize. This one's not 2 hours, which is what your preference is, I know. I'll try to do better next time. But for now, go ahead and give these a try. And, of course, if you have any questions, let me know.